Okay, line P3, learning task number 1, construction and features of three-phase transformers. And I'm going to warn you straight off the bat over here, transformers and motors tend to be two of the absolute hardest subjects inside of third year. So buckle up. Get prepared for this. Just know you're going to have to put in a lot of effort. I'm going to go through materials. You're still going to have to do a lot of study and a lot of practice on your own. Once again, internet is going to be your friend. Look up, worksheets for this stuff. There's tons of resources out there that you could just pick something up and try to solve it. Work your way through. Watch other videos as well. But just buckle down hard into this subject and make sure that you really put in a lot of effort, because it is going to be critical to understanding a lot of the rest of what we have to go through as well. We're going to go and see transformer action that we're going to have inside of motors and things like that. We're actually going to start talking about motor starters. We're going to have to refer back to some of our compensator starters later on. It's all going to be interrelated. Secondly, if you did not fully understand three-phase theory before now, go back and watch those videos again. Spend some time in that module and get a really good grasp on Y and delta type of circuits. Make sure that you know inside of a Y system that you're going to have differing phase and line voltages. Make sure that you know how to calculate your differing line and phase currents when it's inside of a delta system. You're going to be working with transformation ratios that are going to be reliant upon those and jumping back and forth between the two. So just get prepared. It's going to be a lot of work, but it does make sense. Ultimately, at the end of the day, it is a regulated thing. There's no magic at play over here. It's just going to be simply electromagnetism and proper procedures and connections. And a lot of what we're doing is even less so on the involved on the science and more so just making sure we do the correct things in the correct order. Three-phase transformers are constructed one of two ways. Either we can go and take three individual transformers, like what we have over here, and connect them as a bank together. We would call this entire setup over here a single transformer bank. Or alternatively, we can go and have three transformer legs that are going to be wound off of a single core. This would be what we refer to as being a three-phase transformer over here, where we've got a common core and my high and my low voltage windings are all going to be wound around the same legs. This would be what we refer to as a transformer bank, because it's made up of a bank or a collection of three different transformers. Bank, and this is going to just be a transformer, and we are going to go and use the short form TX. Anytime that you see me writing TX, it stands for transformer. Just a shorter way to go and lay this out. On a three-phase transformer, you're usually going to go and have your high and low voltage windings for each phase that are going to be wound on the same leg of the transformer. I say usually because there's one oddball, the zigzag transformer, that is going to kind of break this rule. We're just going to jump around from leg to leg, but 99% of the time you are going to go and see this, where we're going to go and have a high voltage leg composed of many windings, a fine wire, on the same leg or transformer core as what we have our low voltage, which is going to be made up of fewer windings of a thicker wire. You should be able to, at this point, identify when you have got a high voltage winding versus when you have got a low voltage winding. The high voltage is going to go and carry less current, so it's going to be a thin wire. But because it's high voltage, it is going to be a thick insulation. And because it's going to be based upon transformation ratios, it's going to be many turns. Your low voltage is going to go and be the opposite on every single one of these categories. It is going to be thick wire. Sometimes it's actually going to be wrapped bus bars with thin insulation. And it is going to go and have few turns. Not a whole pile of turns that are going to be placed inside of there. Anytime that you open up a transformer, you should be able to identify these off of that. The other way that you are going to go and identify transformer high and low voltage is just going to be off of what we call our standardized markings. And our standardized markings are going to go and have a prefix, which is the first letter inside of there. It is either going to be an H, which stands for high voltage, or it is going to be an X, which is going to go and stand for low voltage. Looking at the cores, construction of a three-phase transformer is usually going to be based around a single core that's going to look like this, made up of windows. Usually it's actually made up of sliced pieces of steel that are going to go and be sliced something like this, and then they go and take this little E section, they shove them together inside of the windings. They'll make the windings usually on a machine, and then they wrap them usually sometimes with what we call the bobbin or the core, which is going to look something like a spool that you would have for, to wrap thread around, just a thin plastic thing. And then they just go and take these two halves and they insert them together. It's going to be a laminated core. We do the laminations to go and reduce our eddy currents, and it's going to be made up of many thin laminations so that our eddy currents, which we're never going to be able to completely eliminate, our eddy currents are able to go and operate on this plane, but because they're insulated with varnish, they cannot go and operate on these two planes. So we're never going to get, cross in the vertical or the horizontal like that. Just we're going to go and get these ones over here. If we take a look at the legs themselves, the legs are going to go and balance out a lot of the flux that we are going to go and generate. You should be familiar with the term flux. This is going to be magnetic lines, or the number of magnetic lines that we are going to go and have inside of a place, which is going to be measured in flux density. At any given moment, all the flux is going to go and be equal. We can, we're always going to go and have what we refer to as balance inside of here. So if I've got a large amount of flux over here, it is going to be, I'll just take flux plus plus, it is going to be balanced out by a flux minus minus, or a flux in the opposite direction. It might be spread over top of two other legs. It might be spread all into a single leg. There's multiple different ways that it's going to get distributed, and it's all going to be based upon where exactly we are inside of that three-phase cycle. Remember, we have three separate waveforms that are peaking at three separate times. We will examine that a little bit more in detail in a couple minutes over here through our figure 4. And figure 4 is going to go and give us these drawings over here. These drawings are going to go and show us instance that they are showing the flux inside of them. I'm just going to zoom in a little bit here. Enhance. Enhance. Excellent. And then we are going to go through each of these ones. Now they're showing us a couple of instants over here. And the first thing that I need to do is I need to go and lay out my 1, 2, and 3 transformer leg. This is going to be transformer leg 1. It is going to be associated with my phase 1, and we're going to go and have that as my phase A. Then I'm going to go and have phase B, go with the black. You should all know why at this point. And phase B is going to go and have this waveform. And then we are going to go and have phase C, which is going to be this one, the third waveform over here, which is going to be this wave over here. And then what we're doing now, based off of that, is we are examining just a point in time. And the point in time that we're examining is right over here. This is going to be instant A. And if I take a look at instant A, on my graph over to the right-hand side, I see that my phase A currently has got a magnitude of 0. Well, if I've got a magnitude of 0, I have got 0 flux lines that's going to be created inside of my line A. And we see that right over here because there are no flux lines inside of my core for A. No voltage, no flux. If I take a look at my phase 2 or my phase B over here, I see that phase B has got flux, but it is in the down direction. It's on the negative side over there. So my phase 2, anytime that I cross the negative side, I'm going to go and see my flux going down in that direction. And I see that simultaneously, while I've got phase 2 over there, phase 3 is at a positive. Not quite at a peak, but it's getting close to the peak there. And so it is going to go and have flux in the opposite direction. If I go and add all these up, like we said before, the flux is going to be completely canceled out. If I were to just go and section across this over here, I would see 0 plus flux in that direction plus flux in that direction, which is all going to cancel out to go and give me 0 amount of net flux. Cool. That illustrates the first one. We're going to step through a couple of other... Whoa! What just happened here? All right, no idea what just happened there. My computer is just being a little bit glitchy, but that's just whatever. Okay, we went through the very first set, which was this one over here. We're now going to go into our second instant. What we're seeing is we're seeing a progression in time. We're moving from instant A, we're moving along as time does, to my instant B. And if I take a look at instant B, we're just going to identify, I'm not going to draw the complete waveforms, but we are going to go and identify where each of these individual waveforms themselves is falling. If I take a look at this, I see that my phase A is currently rising partway through. I see that my phase B, which is going to be my phase number 2, is going to be at a negative peak. And I see that my phase C is going to go and be falling away from its positive peak. We can take a look at that inside of here. We said that anytime that I had something in the negative region, I'm just going to write that up top here. If it's in the negative, it is going to be a downward arrow. Anytime that something is in the positive side of my AC graph, it is going to go and be an upward flux arrow off of this one. This is not hard and fast rules. This would all be based around left-hand rules and how the transformer is physically wound. You could reverse this by just reversing the windings, but we're going to hold on to this convention just while we're explaining these out. Okay, taking a look at this, if I take a look at my red, my phase A over here, my phase A corresponds to this one, my phase B corresponds to this one, and my phase C corresponds to this one. If I take a look at my red is in the positive side, therefore it is going to go and have a upward arrow, and it's not going to be at a maximum value of voltage, therefore it's not going to be at a maximum value of flux. It's kind of an intermediary. If I take a look at my B is the same thing. It's in the positive, therefore it's going to go and have an upward arrow. And if I take a look at my C, I see that my C, I just said B there, I meant C. When I look at my C, which is this one over here, my C is in the positive. And when I look at my B phase is going to be in its absolute negative, and it's going to be the maximum, so it's going to go and have a maximum amount of flux. And we can see that once again, if I were to go and look at the net amount of flux just going across this core over here, I'm going to see that I have 2 units of flux going downward and 2 units of flux going upward. So I end up with a net 0. The next instant that we should be looking at is us moving on from there into an instant that they don't show over here. And we're just going to draw that instant out just for a split second instead of just following through the book. We started out right over here, we went to over here, and then they kind of skipped this one over here, but we're going to go and do this one here just for a split second. And we're going to draw our own lines for that one. If I take a look at this one over here, I see that my phase number 3 is going to be crossing through my 0 right over here. And I see that my phase A, or phase number 1, if I trace that back, is going to be nearing its peak. And I'm going to go and see that my phase 2 is going to be nearing its negative, but it's no longer at a peak over there. What this would look like for us right now is we would have no flux inside of this one over here. I'm actually just going to draw that core out below because it's easier than overlaying over top of theirs. Just give me a sec here. Like that. If I'm going to go and take a look at this right now, I should see inside of here absolutely nothing happening inside of my phase C or my phase 3 over there. I should see that I'm going to go and have an upward inside of my phase A, and I should see I'm going to go and have a downward inside of my phase B over here because it's in the opposite direction. So what I would end up with is I would end up with this loop over here as we move over to that next instant, and nothing that is happening inside of my C phase over here. So what we've done over here, looking at this, is we've started with just a loop going over here in a counterclockwise direction. It's maintained in a counterclockwise direction, but a new loop develops that's going in a clockwise direction. The counterclockwise one disappears in the third instant, but the clockwise one gets established. And then we're going to go and move across to my next step, which is going to be this one right over here. And once again, we are going to go and draw out what we have for our different lines. Phase A is going to be at a positive peak. And then phase B and phase C are going to go and be falling. Or, sorry, they're going to be in a negative, partially up over here and partially up over here. What that would mean is that since my my phase A is at this point at a positive peak, it is going to go and have maximum amount of flux over here. And then I see that the other two are going to go and have flux. Since they're in the negative zone, there's going to be a flux in a downward direction. Once again, we see that the net amount of flux is staying constant inside of here. And this, makes sense that we're always going to see that cancellation out. And we're also seeing, while following through my steps, I saw that over here, I started with a counterclockwise rotation just around this core over here. Then I maintained counterclockwise, but I also set up a clockwise. Then I lost counterclockwise, but I maintained that clockwise. Now I'm going to see that I'm maintaining that clockwise and I'm increasing that clockwise. I'm starting to run another clockwise run over here. And then at the very next instant, which once again is not shown on the graph, we're just going to go and erase this. We will draw in our next instant ourselves. The very next instant over here is going to be crossing right through there where I am going to go and have my A phase falling down a little bit. I'm going to go and have my B phase, which is going to be at a value of 0. And I'm going to go and have my C phase, which is going to be at a negative value over here. If I wanted to draw that one out as a window, and guess what I do? Hold on a second here. Let's just do that. It's going to be smaller. I know, not a lot of space, but they didn't leave us with a lot of illustrations inside here. If I draw this out, I'm going to go and see that I have got 0 flux inside of my B phase because it's crossing 0. And I'm going to see that I have got a maintained positive going flux in the A, and that I've got a maintained negative going flux inside of the C, which carries us over to this point over here. And then if we move one further past that, again, we're going to now go and end up with a maximum amount of current inside of phase C, but it's going to be a negative amount. And then I am going to go and have my phase A, which is going to be positive but falling, and my phase B, which is going to go and be positive but rising over here. I see a positive but rising on my phase B, and I see a positive and rising on my phase A. But I see that I've got a maximum negative that is happening on my phase C over here. So what we're seeing is we're just seeing that every time we never completely lose flux loops. There's always going to be flux somewhere inside of the transformer, but it's always just going to be stepping over and adding another one, maintaining a previous one, then losing the previously maintained one, and then adding another one, maintaining another one, losing a previously maintained one. It's this continuous cycle as we are going to go and see these loops that are basically going to be moving across our transformer, flipping polarity, coming back across, flipping polarity, coming back across, and continuing on like that into infinity. It is AC transformation. That's just what the stuff is going to go and look like. Okay, let's talk about three-phase transformer connections. We've talked about three-phase connections, in basic theory, the fact that we've got Y or delta, but we are now going to go and have Y and delta that we're going to be able to put off of the same transformers. These are going to be, my 4 available transformations are going to be Y to Y, delta to delta, Y to delta, or delta over to Y. When it comes to doing my transformer connections, I'm going to be able to go and take individual units. This over here is either a single leg of a three-phase transformer, or these could be single individual transformers connected as a bank. I'm going to be able to take them like this, and then I'm going to be able to go and make connections. And over here we see what we would consider to be a Y to Y transformer, because we have got both my high voltage side in Y. The high voltage side is going to be everything connected over here, like that, as well as I've also got my low voltage side connected in Y. That's going to be these ones over here. My X's are my low voltage, my H's are going to go and be my high voltage. We're going to go through, the individual ways that we connect these. I'm not going to even bother trying to explain why we've got H2s and, connected together and stuff like that, because we've got a little bit more we want to lay out first, and then we'll look at it. So don't stress about this connection right now. We're going to go through that connection in depth in another couple of videos. The other connection that we do have is going to go and be my delta to delta. Once again, looking at these individual sets over here, the way that they're drawing them right now is just a triangle superimposed over another triangle. And I could look at each one of these as being either an individual leg on a three-phase transformer core, or I could look at these as being three individual transformers connected into a bank, with all of these connections over here being made externally. Either one is perfectly acceptable to us. Generally speaking, we are not going to do a lot of bank connection unless you're working in really high voltage, high power type of industries. If you're working for, an average commercial, even small industrial, you're usually going to go and buy a single unit that's going to have all three windings already on it. And it has some advantages for us to go and buy those three-phase transformers. First of all, because all the cores are shared, we're going to have a slightly higher operating efficiency. We can just get less flux losses because we've only got a single set of cores rather than having my outsides. I've also got a lot less of my shred losses, skin effect, hystereses. Oh man, how did I just forget the R over there? Let me come back to that one. Radiation losses, eddy current, and dielectric losses. That's my shred losses there. We're going to have less of that because we just got less conductor and less core. A single three-phase transformer is also going to have a lesser weight because I got my connection, my core happens through the next core, etc. So I just lose out on having a lot of my iron inside. Same amount of copper, but the iron goes down. It's going to cost less because it's going to be a single unit. You've only got to have a single enclosure, less iron in the core. And it's going to be much easier to install because it's just going to go and have, H1, H2, H3, which you'll identify as your high voltage, X1, X2, X3, which you're going to identify as your low voltage. And all the rest of the transformation connections are going to be made inside. This is big because if you screw up building your own bank, transformers blow up, damage is done, and as well as it takes you a lot longer because you're going to be super, freaked out probably the first time you make one of those connections, and you're going to take a lot of extra time. Time is money in the trade. We just can't afford that at all times, so in a lot of cases, we're going to go with these smaller transformers. There are some advantages to using single-phase transformers connected in a bank, doing something like this. The big advantage for this is that I'm still able to go and operate even if I would lose one of my transformers. I can operate it at a reduced amount of output or reduced kVA in some cases. So if you blow a transformer winding, you might be able to continue on with some processes. You're just going to have to tell your customers, lighten up and wait until you get another one in there. We also have that ability that we can continue operating if this one is broken. Not only are we operating at a lighter capacity, but we also continue operating while we are waiting for a new or for a fix on that transformer core, so we can maintain operation. As well as spares for this one is just going to be cheaper. If we keep around a spare single compared to a spare three-phase complete unit, it's going to be cheaper. In a lot of industrial locations, they do have a parts storage where they're going to go and maintain parts just in case that there's going to be a shutdown because they cannot afford the shutdowns. It just costs them, tens or hundreds of thousands of dollars a day. So we will see these, but like I said before, usually the banks are going to be large industrial. And usually when we're dealing particularly with higher values of voltage, stuff that's going to be over top of that 600 volt range or the 750 that we have inside of our Canadian electrical code. Okay, that's that for